over R compared to what I call K over R max, it's going to end up being slender. So that means when I go through and guess a size, we're going to need to pull off of our graph here a K value and use that in order to come up with our stiffness, our EI, and we'll use that as part of our Euler-Bucking rule. Right? That's part of our equation that we look at for coming up with MC, that multiplied moment. Right? So it's much the same process as what we went through here, that we're going to still graph two terms, our PF over AGH, and it'll be MC over AGH. And I'm still going to go through this exact same process. It's just a little bit more work in coming up with the MC. Yes?
Are we going to need to print off all these tables and bring them to the final? Or
no, so what I'll do is, in the exam, I will print off a select few tables and say, use the attached tables and plot your curve directly on there, right? Because it's a little bit more complex than just, like if you got the tables and you print it off, right? You may calculate these points and come up with this conclusion inside curve and okay, but that doesn't tell me that I know that you've actually plotted the curve and the point correctly. So I'll actually ask you to interpolate the curve and actually draw right on the sheet of paper that I photocopied in the exam. Yeah, so you won't need to print that out as far as what you'll need to bring with you for the exam. Okay, so our example 2 then. Right, same process, just with P delta effects taken into account. Okay, so these are our starting parameters. So here I've given the configuration of the column, so you can see that what kind of configuration we're going to look up with for our K value. And the last one I just said we're going to use a K of 0.9. So here you can actually sort of see the configuration and pull it up directly. Because this one will involve our P delta effects, and we need to take stiffness into account, that means we're going to have to calculate our 1 plus beta b. So I need to know the difference between the dead and the live values. So these are the kind of the results that we're going to get directly off of something like an S-frame analysis. So we're going to start by calculating our PF and our M1 and our M2. And again, the M2 is always going to be the larger of the two. So in that case, M2 will be our top moments, and M1 will be our bottom moments. And so we'll start with those loads. So PF, 1.25 dead, plus 1.5 live, 3.25 kilonewtons. Our M2, again, it's the larger value. 215 kilonewton meters. Under M1. 20 kilonewton meters. Here I don't have to worry about that limit for the M1 to M2 because we're dealing with single curvature. The ratio of M1 to M2 will be positive, so therefore it will not be less than minus 0.5. So I don't even have to worry about that check in this case. You'll notice in this case, I did not specify the column size. So what we're going to do is start by determining the column size. So that's going back to this table right here. Right, so 35 MPa concrete, 400 MPa steel. Right, so this is our table that we're looking at right here. And I'm going to go and find our PF, right, which is 3.8 meganewtons. So let's just scroll down a little bit on that. 3.8 meganewtons is going to come in somewhere around here. So I'm coming across there. And you can see that we have several different options. Right, again, larger sizes, they're all going to work. These lines come right down. So I could go with a 500 by 500, or a 400 by 450 by 450, or possibly even a 400 by 400. Now, I'm not going to worry about the 400 by 400 because, again, this gives us a fairly high reinforcing ratio here. And what that means is that we still haven't accounted for the moment. Right, so like we did in the last example, we have to scale that up. And in this example, again, we're going to need to take into account our P delta effects, which is also going to scale the moment up. So rather than end up way up here on the table, we're going to say, okay, this one here, 450 by 450 seems about right. And it gives us a reinforcing ratio. It's not on the bottom there, but if you actually pull this off, because the numbers have actually changed a bit. 3.8. That's cool. 3.8. Up here, and 450. About 1.5. This table has been updated a little bit from the previous one. And again, we'll pull off a reinforced or an area for our 450 by 450. G 0.2025 meters squared. For this one, we'll get our K value. And so again, looking at the configuration, there's a story above and a story below. Approximate stiffnesses between the beams and the columns are about the same. So this is that 0.9 value right here. Right? So elastic and elastic here. So pulling off the K value, 0.9. And 10.15.2. Our R, approximate at 0.3 times H. Now that we've chosen the size, that gives us 135 millimeters. And so we've got K L over R. And we get 43.3. Yeah, this is less than 100. So we're okay using our simplified analysis. That is where we will end that for today. All right, so the next step then is to go through and calculate that K over our max value. Determine that in this case we do have to worry about slenderness. So we'll go through and calculate our MC. And just like we did before, we're going to calculate that those 2 points based on the horizontal and vertical axis, then find the right curve and see whether it's inside or outside the curve.
So we got our K value just from the diagram there.
Yep.
So we see that, yeah, okay, it's